No nonsense A-level physics lesson 44, projectile motion 1. Yes, we're getting towards the end of kinematics now, towards the end of just predicting where things end up with no consideration of why there's an acceleration. Projectile motion, as we study it in A-level, assumes that acceleration is uniform. So I'm going to make this point up here. Assumes acceleration is uniform. So in this first stage, we're going to say there's no air resistance because that rather messes things up. We might consider air resistance in a qualitative way next lesson, but in this lesson, look, there's no air resistance. There's nothing funny going on. There's only the force of gravity, and it's acting in one direction with a constant acceleration due to gravity on different objects. And there are different ways that you can project. You can have horizontal projection, vertical projection, or diagonal projection. And what that means is that the initial velocity of the object is either horizontal, vertical, or diagonal. So if initial velocity of, that says of body is horizontal, we call it horizontal projection. And what about vertical? Vertical, we call it vertical projection. And what about diagonal? So that's some combination of both. Diagonal, that's probably spelt right. Then we'll have what's called a diagonal projection. They're a little bit more complicated. So we've got our nomenclature sorted out. The initial velocity of the body. It's all concerned with the initial velocity of the body. And there we go. So what does that mean? Well, that means that we're going to use our Suvat equations because we've got constant acceleration. It says uniform there. I thought I decided that I prefer to call it constant. Is constant. Although I suppose technically it's uniform as well. So our acceleration's constant, so we're using our Suvat equations, but here's the tricky bit. If we are projecting horizontally or diagonally, then the acceleration is only going to be acting in one of those directions. So let's keep it simple. Let's imagine that the acceleration is due to gravity, which is down. Any vertical projection is just what we've already looked at. So we have already, come on, spelling. We have already looked at vertical projection last lesson in those two examples that we gave. So last lesson we gave two examples. The example of a car moving towards a garage and slowing down very, very slowly indeed. 0.12 meters per square second deceleration, taking 21 seconds to come to rest. That was horizontal, yes, but the deceleration was horizontal. So that was one-dimensional. All of the motion was along the same line as the acceleration. So we can call that vertical projection. I mean, we wouldn't, it's horizontal, but then we've got a horizontal component of acceleration only. So it's still one-dimensional. So vertical projection is one-dimensional, I guess. That's what I'm trying to say. Whereas here, it was vertical, but there was still only one dimension. The cup was in free fall, downwards, and the acceleration due to gravity was downwards. So in both those cases, it's one-dimensional. That is to say, one-dimensional projection. Nice and easy. So let's now look at horizontal projection. So horizontal projection. Now with horizontal projection, we have the initial velocity of the body horizontal, but the acceleration is still vertical. So let's imagine that we had a picture showing what was happening. We would have our body like this. It would have an initial velocity in this direction, but the acceleration would be in this direction. Oops, let's change that to this. And I'm going to use double-headed arrows for acceleration and single-headed arrows for velocity today. And this is initial velocity, so I'm calling it u. So what's going to happen? Well, I'm hoping that we know that the object is going to follow a curved path. Curved path. And by the time it gets down to some point all the way down here, by the time it gets down to there, what's happened to its initial velocity? Well, the horizontal component of velocity has not changed. The horizontal component of velocity is exactly the same as what it was before. But we've now gained some vertical velocity. So we're going to say acceleration is vertical. Let's just, A is vertical. So horizontal component of velocity is constant. I might move that diagram slightly to make a little bit more room. Let's just move that over to there. There we go. So that's the situation. Now, how do we handle this using our Suvat equations? Well, we know that the object is traveling both horizontally and vertically. So what we can do is we can write down our S, U, V, and A, but in both directions. So S subscript X, U subscript X, V subscript X, and A subscript X. And we can do the same thing in the Y direction. And then we've got our time t. And the object does have independent motion in the horizontal and vertical direction, something we call orthogonality. But the time is the same. The time of motion, the time it's taken for the ball to get from this position to this position here, is the same as the time it's taken for the ball to get from that position to this position here. It's taken the same amount of time to travel that distance vertically as it has to travel that distance horizontally. So with our Suvat equations, they've become two-dimensional, which means that we have to make sure we don't confuse the two dimensions, and I would recommend the use of subscripts. But time is the conduit between them. So we have got horizontal horizontal suvat. And we have got vertical suvat. And in the middle, this section here, time is, and I like to call it the conduit between the two directions. What do I mean by that? Well, I mean that you can calculate the time vertically and then use that horizontally. So let's get an example of a horizontal projection, and we will calculate how far horizontally the object has moved by using information from the vertical. So let's use an example. And we're going to use an example of a ball rolling off a desk. So ball rolling off desk. And you can say the desk is, let's have 0.6 meters high. It's not very high. No, let's have 0.7, which is a horrible, awkward number, meters high desk. And we're going to say that the ball rolls at, what will be a typical rolling speed of a ball? Maybe 0.90 meters per second, something like that. Chose some numbers. So the ball's rolling off a desk. If we wanted to draw a sketch of the setup, what we've got is a desk like this. We've got a ball which is rolling towards the edge of the desk. The ball has an initial velocity entirely in the horizontal direction, which is going to be 0.9, I'll just call it u, 0.90 meters per second. And the ball is going to follow a curved path and is going to land some distance away, and we don't know where that is. That's what we're going to calculate. The ball's going to land somewhere like this. Now, what we can say is that we know the vertical distance the ball falls. The ball is going to fall 70 centimeters. It's going to fall s in the y direction. And we know that it's accelerating with g, but in the vertical direction. And perhaps we want to know the range of that ball. We want to know how far it travels in the x direction. S of x, that's the unknown. So let's write out our suvats. And I'm going to start with the vertical one. So I'm going to do s in the y direction. We know what that is. That's 0.70 meters. U in the vertical direction, we also know it's 0 meters per second. The initial velocity of the ball is 0 in the vertical direction. Now, V in the vertical direction, we don't know. A in the vertical direction, we do know. It's going to be, we could make these negatives because it's going down, actually, couldn't we? We could make that negative 9.81 meters per square second. I'm going to do the same thing. I'm going to make the, I mean, if all the motion is downwards, we might as well call down positive, but we started by saying down is negative, so let's stick with the same convention. That's fine. Now, S in the x direction, that's something that we want. U in the x direction, we know that's 0.90 meters per second. Now, V in the x direction, we do know as well, because a in the x direction is equal to 0. This is what makes it a horizontal projection, is that the initial velocity is entirely horizontal, but the acceleration is entirely vertical. And so we could use the no t equation to calculate v. A is 0, so u squared is just v squared, so u is just v, and we know that that must therefore be 0.90 meters per second. And t is equal to, we don't know. But anyway, let's say we don't know this value of v. It isn't given to us, even though we can work it out. So we want to calculate what the s in the x direction is. And when we want to calculate s in the x direction, we start by looking over in the x direction and saying, which Suvat equation do I use? Well, I've got no v, but I've also got no t. Now, if I did have the v and I was using the no t equation, I still can't calculate s. I can't use the no t equation on the horizontal by itself. Look, v squared is equal to u squared plus 2as. That's the no t equation. This is all horizontal, so let's say x, 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 and x. Let's say we know what v is, but we only know what v is because a is equal to 0. So this whole term here becomes equal to 0. So that just becomes Vx is equal to Ux. And we can't calculate Sx from that because we're timesing it by 0. If you say that's fine, divide through by 2a, you're going to be dividing by 0. You're not allowed to do that. So we cannot use to calculate S of x in this case. We just can't. So what we're going to have to do is use the vertical motion to figure out what's going on horizontally. We're going to use the vertical motion to calculate t, and then use that t in the horizontal motion. So let's use, I have to make a little note of this. So use vertical motion to calculate t. And that way we can use the no v equation, but we've got t. So we can use s equals ut plus a half at squared to calculate what s is. The a is 0, so it just becomes s equals ut. But we need t. So use vertical motion to calculate t. And this is why I say t is the conduit between the horizontal and the vertical. This is why I say that. So we're going to calculate no vy equation. So that's going to be sy is equal to uyt plus half ayt squared. Uy is 0, so this just becomes t is equal to 2 lots of sy divided by ay, all under the square root. Now, obviously, if you're given a uy, it wouldn't be a horizontal projection. Uy must be 0 for this to be a horizontal projection. Initial velocity vertical must be 0 for this to be a horizontal projection. So we don't have to use a quadratic equation. Yes, there's a plus or minus in there, but we're obviously going to take the positive root because negative time doesn't make any sense in this context. So then we plug in our numbers, and we're going to say that 2 multiplied by, now we're falling a distance of displacement is negative 0.70. And you're going to go, oh no, it's that pesky negative again under the square root. But don't worry, because the acceleration is negative 9.81, so those negatives are going to cancel. And if we do that, we get a time. So let's chuck that in my calculator. So 0.7 multiplied by 2, I could have done that in my head, divided by 9.81, and then all under the square root. And I've got 0.378 seconds. I'm going to use 3 significant figures for this intermediate calculation, because this data is 2 significant figure, that's 2 significant figure, so I'm going to be rounding my final answer to 2 significant figures. Well, now I've got the time from stage 1, I can now fill that in, 0.378 seconds. I can now use no Vx equation, which will be Sx is equal to uxt plus half axt squared, but ax is equal to 0. So that just becomes Sx is equal to uxt, which is equal to 0.90 multiplied by our number, which we have rounded to an extra significant figure, which hopefully will guard us a little bit. We get 34 centimeters equals 0.340 meters, about equal to 3.4 times 10 to the negative 1 meters. And that's it. That's how you do a horizontal projection. So you start by looking at what happens vertically, and then you use that to calculate the time, and you use that time in the second stage. So 2 stages. Let me just make a little note of this. So step one, calculate t. Can't even write. Calculate t from vertical motion. And then step 2, calculate whatever else you need. I don't know what you'll need to find. In this case, it was Sx from horizontal and t. So those are the 2 stages. Now, that's because in this example, I was looking for Sx. You don't know what you're going to be asked to calculate, though. Look, you've got so many variables to choose from here. But they're simultaneous equations. So as long as you're careful with the subscripts, then you should be fine. But, you know, I don't know what you'll be given and what you're asked to calculate. So I can't tell you a recipe to solve all of these problems. How many permutations and combinations are there of missing variables? There's quite a lot. Now, I did create a drill spreadsheet that generates questions that you can use to practice this skill, where it shows a horizontal projection. Actually, it shows a diagonal projection, and you've got to fill in the missing numbers. And it works quite well. It's freely available to people who have enrolled in my online tuition. If you haven't, that's fine. Get in contact. I can show you how to do that, or just go to my website to get information. So what about diagonal projection then? Diagonal projection's a little bit more complicated. So perhaps I will talk about that next lesson, and I'll leave this one with this horizontal projection. Yes, we'll talk about diagonal projection next lesson. Well, I hope you found that helpful.